4.1, apply triangle sum properties. So we have some vocab here that we want to start with, and they're going to be, the first three especially, are going to be important to the whole chapter. So the first one is triangle, a polygon with three sides. Probably nothing new there for you, but just a reminder. And I do want to stress the interior angles versus the exterior angles. So when you have a triangle, okay, let me start over with that triangle because it's important I can draw this properly. So here's my triangle. So anything inside here, these are interior angles, okay? So you have your interior inside, which makes sense, kind of like our interior from last chapter between the two parallel lines. So these are inside. There's three of them, okay? My exterior angles are angles outside a polygon. Now, I don't want you to think that this whole thing out here is an exterior angle. That's not what we want to do. What we do is we take an angle that forms a linear pair with an interior. So we take this interior angle that's right here, and we extend this line, and then this outside angle over here, this is the exterior angle, okay? And that exterior angle should be supplementary to the interior angle. So together they add up to 180, okay? So exterior angles, you just take a side, you extend the side, and then this outside angle out here, that's the exterior angle, okay? The last definition, corollary to a theorem. Put this in with your, like in your mind with a postulate, with a theorem, with a corollary and axiom. They're just kind of a category that mathematicians put the different rules into. But for you, as a geometry student, you just need to remember it's kind of a rule that comes out of our other rules, okay? All right, so let's go over some rules about triangles. Many of these you may already know, okay? So this might be one of those sections where it's not brand new and you can handle it without too much studying or too much writing down, but we still need to go over it and make sure we're all on the same page with these rules. So classifying triangles, and there are two ways. Notice we have by sides and by angles, okay? When I say classify, I want one word from each of these categories. So by sides, there's three choices. Scalene triangles have 0 congruent sides, okay? Sometimes we look at the triangle, nothing's marked, they all look different, they're different. Or maybe they all get marked with different markings so that you know for sure nothing is the same length. The next one is isosceles, okay? Do your best to spell that one correctly. Abbreviate it, ISOS, something so I know you're trying to say isosceles. It is a difficult word to spell, and I misspell it at times too, but make sure I clearly can get the message of what you're trying to say. So it says at least, I'm not even going to go with at least, there's exactly 2 congruent sides. Somehow they have to tell us they're congruent. Either they mark them with the same markings like we see here, or somewhere in our proof they become the same length. And then my third way I can classify is if I have 3 congruent sides, and that is an equilateral triangle. And it makes sense because we know from our earlier chapters that equilateral means all sides are equal. So all these sides are exactly the same length, equilateral. So when I say classify by sides, you're giving me one of the 3 words, either scalene, isosceles, or equilateral. Those are our 3 choices for classifying by sides. Now when we classify by angles, I have basically 3 choices again. I can do the 4th one as well. I have acute triangles, okay? Acute angles, there are 3 acute angles, okay? So all of my angles here are less than 90 degrees, okay? And again, this is something you are allowed to visualize as long as nothing looks like a right angle or bigger than a right angle, then you can assume they're acute. Okay, my right triangle has 1 right angle. And I need to also state that means the other 2 angles are acute, okay? And I'm telling you that because sometimes people will say, well, I see an acute angle, that makes an acute triangle. No, an acute triangle needs all 3 angles to be acute, and a right triangle still has acute angles, but it has that 1 right angle, and that's why we call it a right triangle. The obtuse triangle has 1 obtuse angle. Okay, 1 angle here looks bigger than 90. And then the other 2 are also going to be acute just like before. So I get 1 obtuse and 2 acute angles. All right, and my last one is equiangular, which we know back from chapter 2. If things are equiangular, all 3 angles are the same. So we have 3 congruent angles. By the way, they're all acute. And in fact, we should be able to figure them all out, okay? Does anybody remember how many degrees all the angles in a triangle add up to? All right, somebody said 180. Well, if I have 180 degrees and there's 3 of them that are exact, I do 180 divided by 3 and I get 60. So all of these that have the equal marks, they're always going to be 60. And that's true for any equal angular triangle. Not just this one, but all equal angular triangles, all the 3 angles are 60 always, okay? Something to kind of keep in the back of your mind to remember, but that's always true. All right, moving on to page 2. Classify this triangle by sides and by angles. So once again, what I have in the margin is nothing new. It's that box we just went over on the front of the page, but I'm just reminding you 2 classifications, one by sides, equilateral, isosceles, or scalene, and one by angles, acute, right, or obtuse. Okay, so I'm looking at this shuffleboard here, and I have the outside of the shuffleboard is a big triangle. That's what we're looking at, not the individual pieces, but the outside, and I do see a couple markings here. So by the sides, what kind of triangle do I have? Well, I have 2 sides marked congruent, so it looks like it's going to be isosceles. Okay, and I'm going to be honest, I don't really want to dig out my protractor, so I'm looking at these angles and I'm just trying to think of what can they be. A quick measuring device, if you don't even have a protractor with you, is just think of the corner of your paper. The corner of your paper is 90 degrees. If you stuck that corner of the paper in any of these angles, would these angles be exactly the same size as that corner of the paper? Smaller or larger? And I think we get 3 smaller angles. I think all 3 of those angles are acute, okay? So the angles are about less than 90. That's all I'm going to write here. So it looks like, and it's acute. So my 2 words, isosceles and acute for that one. Okay, moving on to checkpoint. It says draw an isosceles right triangle and an obtuse scalene triangle. So we have 2 different pictures we're drawing. Isosceles right. I think it's easiest to start with the right. I draw a right angle. It says isosceles. So 2 of my sides have to be the same. It's going to be these 2 sides because I know this hypotenuse is always bigger than the rest. Okay, so 2 sides the same. That takes care of isosceles, and the corner is the right, so I get an isosceles right. All right, for the obtuse scalene, I'm going to come label this so if somebody looks back at their notes, they remember this. See, can't even spell it when it's written there. All right, isosceles right. All right, next one I'm doing is an obtuse scalene, okay? Just to kind of side note, it's always easier to start with the angle because the angle is so decisive here. So I want an obtuse, so I'm making that a fat angle, okay? So that acute obtuse angle. And I want it scalene, so nothing should be the same length. I think I'm good here. Okay, I want to make sure everybody knows those sides are different lengths. So I'm going to mark this one with 1, this one with 2, this one with 3. And then no one can question, all those are different, so that's why it's scalene. So sometimes remember, it's not how great of an artist you are, it's how you mark your picture. So mark it so they know that. All right, moving on. It says classify this triangle by its sides and determine if the triangle is a right triangle. So we have 2 different jobs here. The first one is to classify it by its sides. So remember, we have 3 choices when we classify by the sides. It can be equilateral, all the sides are the same. It can be isosceles, 2 of the sides are the same. Or it can be scalene, none of the sides are the same. What do we need to know about a triangle to know if it's isosceles, scalene, or equilateral? We need to know the side lengths. Well, when it's on a grid, we can find side lengths by our handy-dandy distance formula, right? So what we're going to do is we're going to take the distance of each side, and then we're going to compare the side lengths, okay? So it looks like the book's starting with RT. So R had point at -3, 3. T has a point at 3, -1. And I'm going to find the distance or the length between those 2 points. Okay, so remember distance formula. It's not going away, guys. I warned you from day 1 when we learned it. It's not going away. Subtract those x's. So -3 minus 3. Subtract those y's, 3 minus -1. All right, we start inside in our parentheses. Dear Aunt Sally tells us parentheses first. -3 minus 3 is -6. 3 minus negative 1 is 4. All right, I'm running out of space fast here. Negative 6 squared is 36. 4 squared is 16. I add those together and I get the square root of 52. Okay. Do I need to go to a decimal? Do I need to get a simplified radical? Stop and ask yourself, what's the job I'm trying to do with this distance formula? The job I'm trying to do is compare the lengths of the sides. So is there any need to be simplified radical or to be a decimal to compare sides? No. I'm going to leave it square root of 52. It gives me a number and it gives me a chance to compare it to another side. All right, moving on to the second side. I'm going to change colors so I can do this a little clearer. RS, R is negative 3, and S is 5, 2. All right, so same idea, different numbers, subtract those x's. Negative 3 minus 5. For the y's, subtract those y's, 3 minus 2. All right, negative 3 minus 5, that's going to be negative 8. 3 minus 2 is 1. Parentheses first, exponents next. Negative 8 squared is 64. 1 squared is 1. 64 plus 1 is 65. Again, I don't need to worry about breaking it down. I don't need to find the pretty. I don't need to get a decimal. I'm just looking for comparison numbers. Okay, third side is ST, and S was 5, 2, and T was 3, negative 1. So subtract those x's. 5 minus 3, subtract those y's, 2 minus negative 1. 5 minus 3 is 2. 2 minus negative 1 is 3. 2 squared is 4, 3 squared is 9, 4 and 9 make 13. So I label this side square root of 13. All right, so now that I have all three lengths, I can go back and say classify it. Is this scalene, no sides are equal? Is it isosceles, 2 sides are equal? Or is it not a right triangle, but a equilateral triangle where all the sides are equal? Clearly all three of my numbers are different. So because all three of my numbers are different, I'm going to call this scalene. Okay? All right. Half my problem's done. Okay? The second half said, determine if the triangle is a right triangle. Now I really want to stress this direction to you. Does it say classify it by its angles? No. It says determine if it's a right triangle. That's all it says. It's a yes or no question for a right triangle. Now, to classify it, we would have to check for right, obtuse, or acute. We do not know anything mathematically right now to check for angles, acute or obtuse. But we can check a right, okay? We can check for that right angle. And to do that, check my margin note over here, right triangles have a 90-degree angle, which means find the slopes and look for opposite reciprocals, because if you have perpendicular lines, then you have a right triangle or a right angle. Okay, perpendicular lines means you'll have a right angle. So we're going to go ahead and count the slopes, okay? I like to count them better than to figure them out, okay? So counting the slopes, I go over to one side. I'm going to start here. Let's just start with RT, okay, because we started with that before. So R to T. So here's R, here's T. I'm going to count up. 1, 2, 3, 4. That's positive when I count up, and I'm going to count left, 1, 2, 3, 4, 5, 6. So I get 4 over 6, which reduces to 2 over 3. The 6 was negative, which went left, so I'm going to need a negative on that one. Okay, let's go to RS next. So from R to S, I count up 1, that's positive, and I count left 1, 2, 3, 4, 5, 6, 7, 8. I get negative 1/8 when I go left, that's a negative. Okay, can't reduce, so I'm good. I have one more to do, ST. S to T down here at the bottom, I count up 1, 2, 3. Counting up is positive, I count to the right 2. So that is positive 3 over 2. Now, so I check, of my 3 slopes, are any of them opposite reciprocals? I have a 3 over 2 and a negative 2 over 3. Opposite by the sign, reciprocal by the flip. So yes, I do have that. So because of that, I know two of my lines here are perpendicular, and that makes them a right angle, okay? So I have a right triangle and a scalene triangle. So a right scalene triangle. Again, I can't stress enough. Run your slopes every time. And then it's either yes, a right triangle, or no, not a right triangle. We're not going for obtuse, we're not going for acute, okay? Third page. Okay, this theorem, especially in the last couple weeks, somebody keeps bringing it up in class, and I keep saying, let's pretend we don't know that yet. Okay, in fact, I just used it on the front page of the notes, pretending we didn't know it yet, but we actually did know it. So this first theorem says the sum of the measures of the interior angles of a triangle is 180. And my guess is you learned this a long time ago in any one math class, I'm not even sure which, that when you add all three angles inside a triangle, they equal 180, okay? If we were in class, I had this tiny little experiment. I hand you a triangle, you tear all the corners off. When you tear those corners off and place them all together, voila, they lay together and they form a line, which is also 180 degrees. So the three corners of a triangle, if you ever have a triangle, you tear off the angles, you put them together so all their flat sides are together, it should form a nice straight line, okay? All right, second theorem. And I can't stress this theorem enough because it's a theorem that we go over, we practice. I put a question like this on a test or a quiz, and people are like, I don't know how to do that, because we forget that we learned this theorem. There's a rule that the exterior angle of a triangle, so this outside angle 1 right here, will be equal to the sum of the measures of the two non-adjacent angles. Okay, so angle 1 over there equals angle A plus angle B. Okay, what's the best way maybe to write this? The outside angle, and this is just kind of to remind yourself, the outside angle equals the sum of the two inside it doesn't touch. Okay, so that's why the non-adjacent, adjacent touches, non-adjacent doesn't touch. So my outside angle is going to equal the sum of the two inside that it doesn't touch. Okay, so let's practice it. And again, I'm going to stress to you, you might forget it, but if you come back to your notes, hopefully you'll see this and you'll be reminded of it. So this outside angle out here is going to equal the sum of these two inside ones it doesn't touch. So 3x minus 9 is going to equal the 73 plus the x. So add the two inside together, it equals the outside one it doesn't touch. Solving for x, subtract x on both sides. I get 2x minus 9 equals 73. Add 9, 2x equals 82, and divide by 2, and x equals 41. So when x equals 41, then we get that. Now, they ask us to find the measure of DCB out here, so I'm actually going to plug my 41 back in. So I do 3 times 41. That's 123. Minus my 9 will leave me with 114. Okay. Let's double check it. If I put x out here as 41, what's 73 plus 41? 114. So those two inside should add up to the same thing as the outside, 114. All right. This corollary, remember, something you can derive from something you already know, okay? Kind of just a side thing. The acute angles of a right triangle are complementary. Okay, we just said, how many angles, what do all the angles inside of a triangle add up to? 180. Well, if you already have one right here that's already 90, that means the other two have to be 90, okay? So what this corollary allows you to do is if you see a right triangle, you can ignore the right angle and just say the other two have to equal 90 and do the math with just those two. You don't have to do it. You can just add the 3 inside up to 180 and go from there. Your choice. But this is kind of a way to maybe shortcut a little bit. All right, last and final page of our notes. We get a story problem. It says, the front face of a wheelchair ramp shown forms a right triangle. The measure of one acute angle is 8 times the measure of the other. Find the measure of each acute angle. We talk about this a lot. If we don't know the other, we like to call it x. They have it marked there. The other acute angle is 8 times that, so we get 8x up here. I know they already had it marked, but I like to kind of go back over where they got that. Okay, so our corollary just told us if you know you have a right triangle, and this already is 90, then you know that the other two should add up to 90, okay? So we could do 8x plus x equals 90. That gives me 9x equals 90, which means x equals 10. So I can plug it back in. That means I have this tiny angle here at 10, and 8 times 10 will give me 80. Do they add up to 90? Definitely, 10 and 80 there. All right, number 2. We don't have a graph. Triangle JKL has these vertices. Classify it by its sides and determine if it's a right triangle. Do we need the graph to be able to classify it by its sides? No, because we can simply do the distance formula without the graph, because to be honest, the graph doesn't help us with the distance formula. So we're going to do 3 of them. We're going to do JK, we're going to do KL, and we're going to do JL. So for JK, I'm looking at -2, -1, and 1, 3. So subtract those x's, -2 minus 1. Subtract those y's, -1 minus 3. -2 minus 1 is -3. -1 minus 3 is -4. -3 squared is 9. -4 squared is 16. Always positive, because a negative times a negative is always positive. 9 and 16 makes the square root of 25. Okay, that's one side. Let's go to the second side, which we said was KL. So K is 1, 3, and L is 5, 0. Okay, distance formula, always subtract those x's, 1 minus 5 squared. Subtract those y's, 3 minus 0 squared. -1, or 1 minus 5 is -4. Got my negative in the wrong spot there. 3 minus 0 is 3. -4 squared is 16. 3 squared is 9. Everything's always positive because anything squared is positive. 16 and 9 make the square root of 25. Starting to see a little bit of pattern going on here. All right, I did J to K, I did K to L, so now I have L to J. L was 5, 0, and J was -2, -1. Subtract those x's, 5 minus -2. And subtract those y's, 0 minus -1. 5 minus -2 becomes 7. 0 minus -1 minus negative becomes positive. 7 squared is 49. 1 squared is 1. 49 and 1 makes square root of 50. All right, so we did all 3 distance formulas. Is this scalene, isosceles, or equilateral? Well, I have 2 sides the same, the square root of 25 and the square root of 25, so, but not 3 sides, so it looks like it's isosceles. All right, don't forget, though, that we have one more part. We need to determine if it is a right triangle, and we use slope for that. Okay, we can still use slope even though we can't count it on the graph, okay? Remember, the slope formula is y2 minus y1, whoops, over x2 minus x1, okay? So I'm going to subtract my y's. I'm just going to go straight up, okay, for these. So I'm going to do 3 minus -1 over 1 minus -2. So important to have your signs, the correct signs, and to stay in the same direction. 3 minus -1 is 4. 1 minus -2 is 3. Minus a negative becomes plus, okay? Can I reduce 4 over 3? No. So that's my slope. Now I'm coming over here to KL. Again, I'm going to just go up both sides here. 0 minus 3 on my y's, and then 5 minus 1 on my x's. 0 minus 3 is -3. 5 minus 1 is 4. And then finally for LJ, going up again, subtract those y's first. Y is always on top. -1 minus 0 on top. And on the bottom, -2 minus 5. That'll give me -1 over -7. So I get 1 over 7. Okay, of my 3 slopes, I've got 1/7, I've got -3 over 4, I've got +4 over 3. Are any of those opposite reciprocals? Yes, the 4/3 and the -3/4 are. That means it's a right triangle. Okay, will you always get right triangles? No, but this time you did, so we get a right isosceles. All right, find the measure of angle 1 in the diagram shown. Well, angle 1 is inside here, but what I do have information on is an exterior. And don't forget, an exterior equals the 2 inside that it doesn't touch. Some of the inside, it's not touching, okay? That's what you have to remember here. Okay, so 3x plus 16, that's the outside one, equals the 2 inside it doesn't touch, 52 plus 2x. All right, subtract 2x on both sides, I get x plus 16 equals 52. Add the 16 and x equals 68. My goodness, let's try that again. All right. I subtracted 2x and I get x plus 16 equals 52. To get x by itself, let's subtract 16. There we go. Subtract 16. What is 52 minus 16 is 36. Okay. But don't forget that's not what it asked me for. It asked me for this angle 1 over here. Well, I know that x is 36, so I could plug it back in here. 3 times 36 plus 16. Well, 3 times 36 is 108, plus 16 is 124. So this angle here is 124. To get angle 1, I can subtract that from 180, so 180 minus that 124. What's that leave me with? 56 degrees. Okay, the other way I can get it is if I plug in 2 times 36 over here, I get 72. Add 52 plus 72 and subtract it from 180. We should get that same 56. All right, last one, number 4. It says, what is the measure of the obtuse angle formed between the ramp and a segment extending from the horizontal leg? Okay, so this wheelchair ramp we were talking about, right? So we had this wheelchair ramp, and it says horizontal leg, that's this bottom one. If we extend it, okay, we keep going right there. We extend it. So right now, remember, we had angles of 80 and 10 from up above, from example 4. It says, what's the measure of the obtuse angle formed between the ramp and a segment extending from the horizontal leg? So here's that extension. So I'm looking for this angle right here. Well, if my inside angle right here is 10, I can do 180 minus 10 and get 170. Or don't forget, an outside angle equals the inside 2 added up that it doesn't touch. And if I do an 80 plus 90, I still get that 170. So no matter how you look at it, I get the 170. All right, so you're practicing these rules about triangles, about the inside angles adding up to 180, about classifying by the sides or the angles, and we're doing the math to go with those, okay? So page 221, 2 through 36 even, and then 43 through 47 all. If you have questions, please let me know.